In this video, we are going to go over the topic 2 solutions, which is hypothesis testing when the population mean is known. Before I get into that, I just want to detail that the project information has its own folder in the main section of Moodle. I will be putting up a video that will go over exactly what is needed from the project, which is, stated in the explanations. But I'm also going to put up sample projects from students in the past over the next week. So the rest of the semester is going to be set up a little bit differently. Since we've already completed topic 1, which you should have done last week, this is definitely a topic not to miss, even though it is pretty heavy on the material and it's sort of vague to begin with, but you should go through this as best as possible before you begin any of the week 10 material. What you're going to find is that there aren't really any notes any longer. Instead, what we have are the hypothesis test reference tables. So those are in our statistical tables folder. So that's the first thing that we're going to be needing today. I'm going to pull that out into its own tab. We are also going to need standard normal tables. And we are also going to need stata, which I already have open. So in addition to that new format, the notes are going to look different as well in that there's not really going to be notes. This is a good thing. This basically means that we learn everything we need to know about hypothesis testing, and with each individual test, we adapt. So for topics 2, 3, and 4, they're testing a claim about a different parameter, and we're using the same 7 steps that we discussed up here, except for we make the necessary changes. Topic 2 will be a little bit different in that we are doing that hypothesis test by hand, but other than that, we're going to be using technology almost 100% for our calculations. The way that the exam will work is that you will be given certain aspects about stata that you'll need to answer questions about. There'll be screenshots and things like that. And p-values and other things that you need will be given to you. So you won't need stata on the exam, but you will need to use it enough to be able to know, how to actually answer those questions as if you did have stata. It's not going to be heavy on memorization. It's just the type of thing where if you have used stata enough for this topic, you will be able to be successful with those types of questions. So I actually want to go over again the steps for hypothesis testing, which is not included in the topic 2 notes. So in the PowerPoint from topic 1 last week, and many of you guys just took your exam at this point, and in that lecture, that's where we have the real crux of everything that we're doing with hypothesis testing. So on this slide, I'm also going to refer back to, but there we go. Looking for this. So the 7 steps to hypothesis testing are not going to change no matter what test we're doing. In the next unit, we are going to skip the picture for a few of them, which is a good thing. Professionally, I would not draw a picture unless it was more for myself. So professionally, skipping a picture isn't going to, make you appear less knowledgeable if you're using statistics out in the real world. So the first step is to read the problem, state your claim, set up your hypotheses, and then draw a picture for your parameters. Then perform an assumptions check. So the way that I do these problems are always going to be written out the same way after the first few problems. The first few problems have A through G to set you up with each of these pieces. But the quizzes and the exam will just have a big blank page, which is kind of scary, but you'll be really comfortable setting up the 7 steps because they are the same every time. So the next step is to find a test statistic, which is again the strength of your evidence. So you're going to label this on your picture and shade the appropriate tails. The sign of your H1 depends on which tail you shade. So this picture here is something that we're gonna refer back to. So then from there, we find a p-value, which is the size of the tail that you've shaded, or tails if you've shaded 2 tails. Then you are to make a decision about the null hypothesis, write a full sentence conclusion regarding the claim. I will expect this on the learning quiz, but on the exam, I'll accept an abbreviated version of this, which we will talk about. And then lastly, a lot of times I put a line down across, so not having a new number, but I would just put a line across in the problem, which we'll see when we do some on our own. This is its own kind of step here. The picture needs to be a new picture. You can't borrow from this picture here. So sometimes people try to double dip and it ends up kind of blowing up on their faces because it's not always the same picture. So we need to draw a new picture here. And then we're going to come up with a confidence interval the same way we did in the last unit, except for whether we're doing 90, 95, 98, 99. That will change based on the specifics of the problem. So that's one of the ways that confidence intervals will change. The other way is that typically confidence intervals will be found using Stata instead of by hand. But for topic 2, we will be doing everything by hand. And again, it's that ownership and sort of initiation to our technology. But it also gives us a really, really good understanding of hypothesis testing and what it is. So I just took a moment to fix this picture. I did fix it in my original file, but unfortunately it had already been uploaded. So let's have a look at the 2 documents in topic 2. The first one is just a plain document entitled Estimating a Population Mean with sigma, which remember is our population standard deviation, known. In the real world, this doesn't happen very often, but there are some scenarios that it could. Personally, I've never done this test, but that doesn't mean that you may not face a situation where it applies, but it's pretty unlikely. However, this is a good first test to begin with because we know the z distribution well. So I always start off with this one by hand, even though it's not the most realistic test that you could find in the real world because of that experience that you have with the normal distribution. So a study by M. Chen et al. Titled Heat Stress Evaluation in Worker Fatigue in a Steel Plant assessed fatigue in a steel plant worker due to heat stress. A random sample of 30 casting workers had a mean post-work heart rate of 78.3 beats per minute. Using a 0.05 significance level, so that's our alpha value, does the data provide sufficient evidence to conclude that the mean post-work heart rate for casting workers is greater than the normal resting heart rate of 72 beats per minute? Assume that the population standard deviation is 11.2 beats per minute. So I read this problem out loud because I want to emphasize that I will actually be reading all of the problems in detail. It's really easy to kind of become a robot and just kind of circle certain numbers here. But this first step is probably going to take most of your time, especially when topic 2 isn't just given on the handout. When it's a quiz, you don't know which problem it is exactly. You have to think about it. So I'm going to hop over to the reference tables before we start approaching this problem, just to see what we will have with us on our exam, as well as what you should understand that you have with you, and also what we should end up feeling like we need to memorize. So we're going to be doing 8 different types of hypothesis tests. So this is 1, 2, 3, 4, 5, 6. I consider this one the same test. 7 and 8. These are in order in which we do them in the course. So that's why some of them kind of seem like they have, larger blank spaces. So this left column here is actually topic 2, and I would probably write topic 2 on the top of this. So what each of these have are what your null and alternative hypotheses could potentially be. It is very, very, very important that a number goes here. So I'm actually gonna go to my BFF Paint, and I would write these down on here. So this would be topic 2. I would put this in colored writing. Let's see. Nope. Yeah, that one's not bad. Okay, so then I would know, okay, this column is from topic 2. So even though on the exam, it's not going to say specifically this is a topic 2 question, you're going to start to make associations. And those associations are going to be, you know, kind of pathways in your brain that you make to help you start a question from a big blank page, because that can be very scary. But normally this is a very high scoring unit because we get a chance to get good at something, which I feel like so far we haven't had the chance to do in this class, because we learn a concept and then we move on and just keep going. It's a very fast-paced class. This right here that I'm boxing, it is very important that a number, okay, so a number goes in place of this mu naught here. So you can never put mu naught. That would be very incorrect and incomplete. So we're still new to this, no expectations at all, but I like to mention that because it's something that you should have written down on the reference tables you use with you. Of course, you'll get a blank one when you go to your test, but this will be given to you on the exam. So this goes straight across because they're the same for both types of hypothesis tests. The assumptions are very, very, very similar, with the one exception of our fake assumption. So we've talked about this with hypothesis testing. This is the same assumption here, and this really is a fake one because it's just leading you into which type of test to do. So from here, the major difference that we have is the distribution. So if we have a mean with the population standard deviation known, we know that we have the preciseness that the z-distribution brings. If we're testing a claim about a mean and the population standard deviation is unknown, then we use the t-distribution because we don't have that preciseness and we need the distributions to be heavier in the tails. Regardless, and I am going to freehand this, and it is going to be probably pretty bad. Oh yeah. That shouldn't see the light of day. Regardless, however, we're still going to be drawing the same shape. So let me get a bottom axis. Maybe that will help. Probably not. Oh yeah, that's not bad. So no matter which one of these we're doing, we're still drawing a bell curve shape because remember, as the sample size gets closer to 30, the t-distribution is going to start to look like the normal distribution a lot. And as it goes to infinity, that sample size will eventually have them looking exactly the same. So I'm going to highlight this. We will be using this formula. However, we will not be using this one. I put this down here because it's important to me that you know where things come from. They don't, you know, it's not just magic, hocus pocus data. But I wouldn't cross this out on your own sheet. But if you did, it's not a big deal. But you will not be using this. You could do this one by hand. You'd run into an issue at some point. But you could do that one by hand. However, the major breakdown that we're going to have here is using stata. So there's two different cases for using stata. I'm not going to get into them in detail today because we're expected to do these by hand. However, I am going to double check my answers using stata. So I'm going to utilize stata to its capabilities even though we are going to be doing these by hand. So one thing I would put down here as a first timer for our hypothesis test is that the confidence level will change based on the significance level and tails in the test. So our confidence level will be different most of the time, I would say. So alpha is 0.05 most often, but it can change in a number of different situations, which we'll see on this first handout a little bit. But I kept the alpha level calm for a while. Okay, so I'm going to window this down, and this is now what it would look like again on your test. Feel free to have some things that you want to come into the test and write down right away. You've got a while, but so I read this problem already, and when I go over to the actual, my actual work here, I underlined and I made some notes and I made some special notes. I put in some notation here. So I didn't just go, just plopping out numbers from the problem, which happens pretty often, even people that are, pretty thorough, just because they start to get into a routine, which can be dangerous. So, like I said, this first problem gives you A through F. I guess it's not A through G because steps 3 and 4 are put together. It gives you those steps separately. However, a problem normally looks like this, which is a big blank page. I guess this would be a better, yeah, there we go. Normally looks like this. It's a big blank page. But again, the 7 steps are the same every time, so it's not as terrifying as it seems. But let's get started. So I'm going to go through a few of these and leave 1 or 2 to your own devices and questions to ask me if you're having any issues. Step 1 we practiced pretty thoroughly in topic 1. So if you skipped over topic 1, you need to know how to do this step very clearly. A lot of this is based on what we do in step 1. You see there's a lot of work down here. So you do want to make sure that you have the topic 1 stuff down. So A says state the claim and hypotheses and then draw the correct distribution in part C. So when we read this problem, one of the things I underlined was, does the data provide sufficient evidence to conclude that the mean post-work heart rate for casting workers is greater than the normal resting heart rate of 72 beats per minute? So what we want to do is see if this is statistically high enough so that it is different than 72 beats per minute. So we know obviously 78.3 is greater than 72, but is it higher so much that it's statistically different is our question. So the claim is that the population mean of all workers ever, the metal workers, casting workers, is greater than 72, and this does not have equality to 72 in any way. So for that reason, this is going to be H1. HO is always going to have an equal sign, and you can be robotic with this one. I give you permission. It's just mu is equal to 72. These two are not opposites, and that is okay. The most important thing is that they can't be true at the same time. So both of these couldn't be equal to 72, but H1 should never have equality in any way whatsoever. So step 2 is an assumptions check. Random is stated, so we do pass that. Our second major requirement, so if this was me on a quiz or test, I would hop over to my reference tables and say, okay, here, I've identified this kind of test. The population standard deviation is known, so I would eventually hop to this column specifically. So normal population, we don't know, and we don't have the data to test for, but we do have a sample size of 30, which is our minimum that we can have in order to pass normally distributed data by the central limit theorem. And so lastly, sigma is known. So we're testing a claim about a mean. Sigma is known. So when we hop down to step 3 here, which I didn't do yet because we didn't discuss this specifically, you would have just a blank normal distribution. It's not very curvy, but you wouldn't have anything written on here at all. It would just be a blank normal distribution. So it would just look like one of these, no markings on it at all. So this is one that I would typically use from blank. So if you want to do this without scanning anything in, I find that to be kind of brave. I mean, just typing things into the computer. You're going to need to use a picture, and I would probably use my BFF Paint. So this distribution would originally have nothing written in it, on it, or around it. What I would add to it, however, is that the mean is 72. That's what we're assuming is true, which is kind of the basis of hypothesis testing, if you remember that from topic 1. We start off with this completely assuming that HO is true, and then we see, hey, if this is true, how crazy is a mean of 78.3 just by chance? Because remember, this was just a sample, it wasn't a census. So the other thing that I note right here is whether we have a left tail, a right tail, or a two-tail test. So I would go back to my PowerPoint picture here. This 100% depends on the sign of H1. So if H1 has a not equal to, then you will have two tails in your picture. And don't shade them yet, you're going to wait to shade them. If H1 has a less than, then the shaded tail will eventually be on the left side. If H1 has a greater than, then you eventually will shade the right side. A trick that you can do until we understand why this is the case is that the sign points towards the tail. So less than points towards the left, that's this left tail over here. Greater than points towards the right, that's this right tail over here. So in this case, we have a greater than, so that means this is going to be a right tail test. This is important to write in because sometimes you'll get down here and you'll go autopilot and you'll just start shading stuff. It'll eventually happen. So the third step is to find out, well, how strong is our evidence for or against this being true here, this 72 being a mean. So the formula for the z-score I would get from right here, and again, this is the only one that we're doing by hand, is the sample mean has to come first, very important, minus this claimed number, the 72, divided by the population standard deviation divided by the sample size. When you do this, you should get 3.08. So please make sure that you're actually plugging this into your calculator and getting 3.08. If you're not getting this answer, you probably are either doing too few steps, I would do a bunch, or you need to just put your denominator in parentheses. So once we have that z-score, we label it on our distribution. So I did label this one. This has a z-score of 0 right here if I found this one because it's right smack dab in the center. So think about now standard normal blending to this situation. So now I'd say 3 steps up is well over here somewhere. This is not always going to be drawn to scale, but it should be pretty close. So you shouldn't have it shaded way over here. I mean, that would be more like 10-15% than it would be the p-value we're going to get. So I just kind of pick a place that feels right. So 3.08, I put a line up, and then H1 is greater than, so it's a right tail test. Oops, my bad, I'll put a note on that. It's a right tail test. So we would shade the right tail. If it was truly left-tailed, we would shade all this other stuff here. So I'll fix that. So now what we need to do is find out how big is this shaded area. And to do that, we are going to need the standard normal distributions making their comeback. So I have a z-score of positive 3.08. So my column would be the 0.08 column. And so my value that I'm getting for the area is 0.9990, which remember, this is always the area to the left. So 0.999 is going to be this area right here, which means the shaded area is 0.001. So unit 3 doesn't completely go away with that normal distribution stuff. This shaded area right here is the p-value. The p-value by definition is the probability of getting a test statistic at least as unusual as the one that we've observed. So there's not a lot of area to the right of this exact moment if we did a tiny little piece because the curve is so close to the bottom axis at this point. So the question, again, we're ultimately looking to answer is the heart rate of these metal workers, is that greater than the resting heart rate of 72 beats per minute? So this is not the probability that this is true. It's the probability that it's at least 78.3. And I know that sounds very unusual and like it doesn't add up completely. However, it is how hypothesis test works. It is legit. And it's a very detailed piece to explain. So this tells us our likeliness. Okay, so since the p-value, so now we compare our p-value to our cutoff of alpha, 0.05. So since the p-value is less than 0.05, the p is low, we reject HO. That's the saying that people will typically have memorized. If the p-value is low, we reject HO. And so then from here, we would support H1. And our claim also happens to be H1. So this is why it's a two-part decision. Because if your claim was HO and you reject HO, well then you're saying goodbye to the claim as well. However, we're going to support the claim that the true mean post-work heart rate of steel plant workers is greater than 72 beats per minute. So we found that statistically, even though we didn't have a census, we have pretty strong evidence that they do have a higher mean heart rate. I mean, of course, you can look at it and say, yeah, it's higher, but that's not as good as saying, hey, I ran a statistical test and, I found at this 0.05 level, there is evidence to suggest. And so maybe they don't expect the metal workers to have a higher heart rate. Maybe they need to, redesign their working. I would imagine that they would have a higher heart rate. However, there's lots of data that needs to be tracked in order to keep track of things like health and safety for both a human level as well as for things like insurance and stuff like that. So now to step 7, which obviously looks like it's got a lot going on. But the good news is that not all of it is new. As a matter of fact, the only new thing that we're actually going to have is what confidence level we set up. So I kept with my left tail theme. So I gotta make a note of this when I upload this. So alpha is how much we're willing to allow in the right tail. So 0.05 is how much area we are willing to allow here. But confidence intervals are symmetrical. So we actually need to create a tail of our own. So when we do that, we end up putting 5% area there as well. And so what that ends up resulting in is a confidence level of 90%. So the error and the confidence level are the same exact thing that we did last unit. So this is the critical value for 90%, population standard deviation divided by the square root of the sample size. So when you're finding this critical value right here, we want to know either this z-score that has 0.05 to the right or this z-score that has 0.05 to the left, and then we make it positive. So when you look this up in the tables, you're going to find two that are equidistant. So I'm going to look up the low one because I know where that is. All right, so this one is equally between 1.64 and 1.65. I've been requesting that you guys use 1.64, although if you use 1.65, it's not a big deal. But this number is actually closer. Now we can ask Stata. So let's have Stata tell us. We have the area. How much area we have there, and it's negative 1.6448. So it is closer to 1.64. From here on out, I do want you to use that, but you won't need to worry about this because this is the only one that we do by hand. So when you plug in these values you end up with this confidence interval here. So I am going to assume that the confidence interval part is at least decent. And so then you will only find the MVD if you reject HO. Okay, so I'm going to write this somewhere. I feel like this isn't written in enough places. If you reject, remember, we enter into the problem saying, hey, this is true. Right here, this is true. So when you get down to the bottom, if 72 isn't here, you want to say, okay, well, 72 is wrong, and by how much? So this is actually the same thing that we did with the MVD in Unit 3, but the 72 is just buried in a whole bunch of stuff because the problems are pretty long. So the minimum verifiable difference is 2.95 beats per minute. So maybe there's a law that says, these type of workers, aren't supposed to have, an elevated heart rate for more than X amount of hours per day or something for their own safety. They would really need to look into this and test this and prove that that is, meeting compliance. This is definitely a unique situation, but this is a problem that I think we've seen before. So I'm pretty sure we did a confidence interval thing on this. So I like to bring it back and make it relevant again. So this finishes this question. The video is getting a little long, but this does completely finish this question. I'm going to do 2 more of them. And so I want to give you guys a chance to, if you want to listen to all of them, to go through them. And I'll leave one for your, your own recognizances here. But let's look at, I want to make sure I do one of them. Yeah, all right, so we'll do 2 and 3. So number 2, I'm going to give you a second. I would pause and read this problem. So I, for the most part, would try to have this be what you have next to you until you're ready to look at my solutions. And start with this for as long as you can, the blank page, and then go over here when you need to. But try to rely on the solutions as little as possible because you'll eventually need to be 100% independent. But I do offer, just like I did a practice exam for the last test, I do offer practice problems. So I don't have STATA stuff specifically, but I do have lots and lots of practice problems for you to work with for this test. So you'll get a lot of chance to practice on your own, but try to be as independent as possible. As sooner the better. So this is a situation where they had a maze. They had mice run through this maze, and they kept track of every mouse that ever ran through the maze. The population mean was 18 seconds, and the population standard deviation was 2 seconds. So this is a population standard deviation, so that should start to clue you into what kind of test to do. It is pretty unusual that we get this scenario, but it's definitely something that will happen. So be prepared for that. One researcher thinks that a loud noise will cause the mice to complete the maze faster, but another coworker disagrees. So they test this. The researcher makes a loud noise for 10 randomly selected mice that are going through the maze, and a mean completion time is 16.8 seconds. So they did finish it on average less, but is it less, is it smaller of a number by 18? Enough to include that it's statistically different. So this is where our confidence or our significance level comes into play. And the claim that we're specifically testing is that the mean time is the same with or without a loud noise. So we're testing that the mean is equal to 18 no matter what. So this is a new population that we are introducing here, which is one thing that you can use hypothesis testing for. So that's actually what we did in this last question. We compared the steel plant workers to the normal population. So the claim is going to be that the mean is equal to 18, that the mice finished the maze at the same speed on average. And this is going to be HO because you can't be more having of a quality than having an equal sign. So here we have an equal to 18. Not equal to 18 is going to be our alternative So whenever your claim has an equal to, it's going to be equal and not equal to. Our assumptions pass because we have a random sample and they tell us that the completion time is normally distributed. This is probably true, but if this was myself doing an analysis, I would ask them, like, what evidence do you have that this is true? And they would need to probably show me a hypothesis test that they did really quick, as Shapiro will probably. And then sigma is given. So we're going to find the z-score and the p-value in the same exact way. So I did kind of ignored my picture. So I draw a z distribution. 18 being the absolute truth goes right in the middle. And since we have an H1 with a not equal to, that means this is a two-tailed test. So what this actually means is, so think about this one, and this is where I talk about the tails. If the mean is equal to 18, then that means that it could be off on a low end, or it could be off on the high end. So right, if it was maybe 10, we'd say, whoa, that's way too low. And I'm sure statistically it would be too low too. If it was 25, maybe, you know, they heard the noise and they panicked and they stopped dead. That's pretty far out there. And so there's two ways that you can be not equal to 18, on the low end and the high end. So I'm going to continue this explanation for other problems as well now that we've gotten this one. So this z-score formula is the same as previous z-score formulas in calculations. The z-score that you get is negative 1.90. So I typically only write down the observed one, but I did for this problem write down the mirrored version as well, just because this tail has the same size as this one. Not to scale, it's okay, it's not too far off. But the area to the left of negative 1.90, well, whoops, I lost my normal. So negative 1.90, that's 0.0287. However, we have two tails. So we need to double this value. So this is 0.0287. This one is 0.0287. So when you combine them both, overall you get 0.0574. So if the p is low, we reject HO. But if the p is high, the null will fly, meaning we go with it. So since the p-value is greater than our cutoff of 0.05, given up here, then we fail to reject HO. This means that we have sufficient evidence to reject that the mean time for the mice to complete the maze is faster with a loud noise. Maybe, you know, if we kept on collecting more data, we got a bigger sample size or more different mice or something, maybe that might be the case. However, we're not saying absolutely incorrect, wrong. We're just saying at this time, we don't have the evidence to reject this being true. So, you know, maybe it's pretty close to our cutoff. So maybe if we got more mice, we'd end up getting mice that were faster if they heard the noise. However, as of this point, based on these 10 mice and this data that they've collected, we don't have any evidence to reject that. So the confidence interval now is already symmetrical because we're already two-tailed. So we already have two tails in our test, and alpha is how much we are allowing in the tails. So that's how big we're allowing the tail to be. So 95% is left over after we have these two tails together adding up to 5%. The confidence interval is going to be exactly the same way as Unit 3. The critical value is 1.96. So we end up with a confidence level of 15.56 to 18.04. Since 18 is inside the confidence interval, this supports failing to reject HO, and HO says that the mean is 18. So our 95% confidence interval supports 18 as still viable. Now, 18 does fall towards the end of this confidence interval, but that doesn't matter because at the beginning we set this significance level. So it's really important to set this first because this is kind of how far off you're willing to be without So it's basically how far off you're willing to be. So when we get down here, that's the value we've set as our acceptance, and 18 is still inside. It's pretty shady, but sometimes people can go back and modify their values if they want to get certain results. That's one reason why it's easy to distrust statistics, but you guys will have more statistical knowledge than the average population 10 times over. So you guys will have the ability to just question, well, why did you use an alpha of 0.1 or why did you use alpha of 0.10? And they'd better have a reason because 0.05 is pretty much the industry standard. We're going to change ours to 0.01 a few times just because it will happen. Sometimes things that are more, life dependent will want to have different values. But yeah, let's move on to the next one. So this is the last one I'm going to go over. Yeah, to my knowledge, this one's pretty plain vanilla. So number 3 is real data. The U.S. Census Bureau conducts nationwide surveys on characteristics of U.S. households and publishes them in current population reports. The following data is a random sample of the number of people per household for 40 households. The average, the article also states that, an article states that the average household in the U.S. has at least 3 people. Assume the population standard deviation is 1.2 people. So we're going to need Stata to find the mean and standard deviation, but I'm finding some people say, hey, can I find the mean and standard deviation using, my own, my calculator or something like that. That's perfectly fine if you don't have to do a Shapiro-Wilk test. So for this one, we won't because of our sample size. So I'm going to pause here and enter the data, and you do the same as well. So to confirm that you've entered your data correctly, I did this 2 separate times. So the sample mean should be 2.825, and the standard deviation of the sample should be 1.483. Now, we are going to be using the population standard deviation here. However, I did use the sample standard deviation just because that's important information to know. So it could be confusing, but you should kind of be able to work them separately, in my opinion. So let's see how small I can make this without it getting mad. The output might look funny. So they're claiming that the mean is at least 3 people. So that's a greater than or equal to, which for a claim is kind of a pain in the neck because HO has to have equality, and our claim does have equality. However, it doesn't have just an equal sign. So what you have to think about is that this is going to be HO is going to be that mu is greater than or equal to 3 in disguise. So our H1 has to be less than in order for these two to not overlap in any way. Because even though this has just an equal sign, it's still greater than or equal to in advance or in disguise. So now notice how I'm setting up my page. I do this the same every single time. So I do 1, 2, 3, 4, 5, 6 with the picture over here below 2, a line, and then number 7. So I always do it this way. I would like you to do it this way as well. However, it's not required. It makes it a lot easier for me to grade, and sometimes if I really can't find or follow your work, you could not gain full credit. But for the most part, sometimes people make small adaptations, but I think this is a good setup. So random, it states this, so we'll take it. And then we need a normal population, or we need the population to have the sample to be at least 30, which we do have. It's 40. So we can pass this. We don't have to check any normality. And then we can actually get to the problem. So I'm going to skip through finding the z-score and the p-value because these are things that we did in Unit 3 pretty repetitively. If you're still having problems with this, you're going to need to be able to do one of these on the learning quiz. But I'll be honest with you, it's not on the test or the final. So technology is the way of the lands, and the scenarios I want you to focus on are the ones that are more likely that you'll encounter. So this one will get the X for the exam. But you should still be able to find this. It will still cause you trouble if you are unable. So the p-value is greater than 0.05. So the p-value is high, the null will fly, which means we go with it, aka we fail to reject. So what I want you to think about this is that the closer our test statistic is to this, the more likely it is that that's true. The farther it is away, the more far-fetched that this is true. So these pieces all work together in a sensical way, but it's really hard to get to that point until you've done at least 2 topics on it. So this is pretty close. I think it makes sense that we say, hey, this is reasonable. And so even though this is greater than or equal to 3 is still part of this. So since we fail to reject HO, we support the claim. So we're saying, hey, check mark, we're going with this one. But this is also our claim. So we're going to support the claim that the mean household in the US is at least 3 people. Now the confidence level, this was originally a left-tailed test since H1 had a left less than. So we have, let's check, do we have, yeah, a significance level of 0.05. So since we have that, that's in our left tail, we have to double it to make our confidence interval symmetrical. And our resulting confidence interval will be 2.5, 3.1. So what we would actually need to say here is that since 3 is inside this confidence interval, this supports failing to reject HO. So I will add that to our notes. So I do actually want to start this problem because it's going to utilize a normality test. So I'm going to pause and enter this data. Please do the same. And you'll know that your data is entered correctly because you'll have a mean of 52.25 and a sample standard deviation of 6.51. So this problem is analyzing the diagnosis age for early onset dementia. So 20 people that were given a diagnosis were their ages were recorded, and maybe they're making a pamphlet or some kind of other instructional information, or they just want to make a statement. What is the diagnosis age, the mean diagnosis age for all people with early onset dementia? Is it 55? Is that the mean? So that's going to be that mu is equal to 55, which will be HO exactly. Can't have a quality more than an equal sign. H1 is going to be a not equal to. Random should pass. So I am missing an equal sign, or a check mark, I mean. So the second part of the assumption says that we either have a sample size of at least 30, which we do not have, or that we have a population that is normally distributed. In order to have evidence that our population is normally distributed, we need to run the Shapiro-Wilk test. So I have my data in var2. You should really be naming these things. Obviously I should be as well, but to do the Shapiro-Wilk test, we're going to go to the distributional plots and tests, Shapiro-Wilk test for normality, old variable out of there, var2. So the p-value for the Shapiro-Wilk test is 0.1223, which is greater than 0.05. So this passes normality because in this test, HO is evidence of normality, and H1 is evidence against normality. So if it's higher, we're supporting normality, so this passes. You need to state this p-value in your assignments, on your, your project. You need to state this. It's really important that you check this because if this doesn't pass, you actually can't use the type of test that we're doing. There's another test that's pretty close, to be honest, but we would need to use that one instead. It's called a non-parametric test. So I'm going to leave the rest of this problem. I really just wanted to go over the normality. So I'm going to leave this up to you guys. So please feel free to email me if you have any questions. Please make sure that you've gone through topic 1 in its entirety, even though it is very vague. And please make sure that you try to do these by hand with at least 90% accuracy before moving on to the next topic. As always, please feel free to email me if you have any questions.